Hi and welcome to this video on solving second order ordinary differential equations. This video is primarily aimed at students revising for their A-level maths and or further maths exam, as well as students preparing for or partaking in a STEM-based degree. If this is the first video from my collection that you are watching, you may want to take some time to watch my introductory video. This should give you a better idea of how to get the most out of these videos. If you have not already watched my video on solving first order ODEs, you may wish to do so before watching this video. So let's have a look at second order ODEs. The general form of a linear second order differential equation is d2y by dx squared plus dy by dx times p of x plus y times r of x equals q of x, where p of x, r of x and q of x are all given functions of x. The general solution of a linear second order differential equation, which are often referred to as GS, is the sum of two parts. Firstly, a particular integral, which are often referred to as pi, which is the solution of the differential equation, and a complementary function, which are often referred to as CF. So here's some terminology. ODEs are either classified as homogeneous linear ODEs, or non-homogeneous. ODEs are homogeneous if they have q of x equal to 0, and are non-homogeneous if q of x does not equal 0. The general solution for homogeneous equations is actually just the complementary function. So g of s is simply CF. So let's have a look at finding complementary functions. To find a complementary function, we need to construct an auxiliary equation. The auxiliary equation method is the main way we find the complementary function. We construct an auxiliary equation for the homogeneous version of the ODE. So if we have the ODE a times dy by dx plus by equals q of x, so the first order differential equation. Then we have the auxiliary equation am plus b equals 0. This has one root, which is m, so we have a complementary function of y equals c times e to the power of mx, where c is an arbitrary constant and m is our one root. Moving on to a second order ODE. So for an ODE of the form a times d2y by dx squared plus b times dy by dx plus cy equals q of x, we have the auxiliary equation am squared plus bm plus c equals 0. This is not as straightforward for giving us a complementary function, as there are 3 separate cases which need to be considered, and each of these separate cases leads to a different complementary function. So let's have a look at these in more detail. So for our first case, this is when the auxiliary equation has 2 distinct roots. Let's call them m1 and m2. Then we have the complementary function y equals a times e to the power of m1 x, which is our first root, plus b times e to the power of m2 times x, which is our second root, where a and b are both arbitrary constants. The second case, This is where there's one sole repeated root. Let's call this m. Here we have the complementary function y equals e to the power of mx, all times by a plus bx, where here m is our root and a and b are both arbitrary constants. So in the third case, this is when there are complex roots, i.e. the roots of the form m1 plus or minus I times m2. Then we have the complementary function y equals e to the power of m1 times x, where m1 is the real part of our complex roots, times a times sine of m2x, where m2 is the imaginary part of our complex root, plus b times cos of m2 times x. Again, a and b are arbitrary constants. So we are now perfectly able to deal with homogeneous second order ODEs. We're now able to solve them. So let's have a look at an example. d2y by dx squared minus 4 times dy by dx plus 3y equals 0. As we can see by the fact that this equals 0, we have a homogeneous second order ODE. Here we have the auxiliary equation m squared minus 4m plus 3 equals 0. We can then factorise this to solve it, and we get m minus 3 times m minus 1 equals 0. So we get two distinct roots. These are m1 equals 1 and m2 equals 3. Hence we have two distinct roots. So this gives us the complementary function of the form y equals a times e to the x, as m1 is 1, plus b times e to the power of 3x, as m2 is 3. As this is a homogeneous equation, our general solution is just equal to our complementary function. So we get a general solution of y equals a times e to the x plus b times e to the 3x, where a and b are arbitrary constants. This is our general solution. Similar to when solving first order ODEs, we can find a particular solution by subbing in initial conditions and solving for a and b. Now let's look in more detail at finding particular integral. In solving the particular integral, our aim is to find a function of the form y equals f of x, which when differentiated once or twice and mixed with different coefficients produces the given function q of x, which did not equal 0, as we only look for particular integrals for non-homogeneous ODEs. So, if the function q of x in our original ODE was a polynomial, then we can try using a function f of x which is a polynomial of the same degree. So we could try y equals ax plus b for any first order ODEs, and we could try the polynomial y equals ax squared plus bx plus c for any second order ODEs. If the function q of x was an exponential, then we could try the function f of x as an exponential of the same power, i.e. y equals a times e to the power of mx, where m is the same power. If the function q of x is a mixture of sines and cosines, Then similarly we will try a function of f of x, which is a mixture of sines and cosines, e.g. y equals a times sine x plus b times cos x. In all of these above cases, we differentiate once and then twice and substitute these back into the original equation and solve so that we get values for a, b and c if applicable. In some cases, the usual function y equals f of x will not work as it is contained in the complementary function. In this case, we would try y equals x times the function f of x. So, if we are dealing with a non-homogeneous second order ODE, we are now able to solve it. So let's try an example. Let's try and solve d2y by dx squared minus 4 times dy by dx plus 3 equals 6x. Again, we want to solve for y. As you can see by the fact this is 6x, this is a non-homogeneous ODE. Any of you who are particularly eagle-eyed will notice that this is the same second order equation we calculated earlier, except before we looked at the homogeneous version. This means that we already calculated the complementary function for this ODE. Our complementary function was y equals a times e to the power of x plus b times e to the power of 3x, where a and b were arbitrary constants. So all that's left to solve is finding the particular integral. Here we have that q of x equals 6x. This is a polynomial, so we can try a function f of x which is also a polynomial of the same degree as the ODE. So let's try y equals a x squared plus bx plus c. We then have to differentiate this once and then again, so we get dy by dx equals 2ax plus b, and we get d2y dx squared equals 2a, and we then have to sub these back into the original ODE. So subbing these back into the original ODE, which was d2y by dx squared minus 4 times dy by dx plus 3 equals 6x, we get that 2a minus 4 times 2ax plus b plus 3 equals 6x. We can simplify this further to get 2a minus 8ax minus 4b plus 3 equals 6x, which equating coefficients gives us that a equals minus 3 over 4 and b equals 3/8. We now have the values of a, b and c we can assume is 0, so we get that our particular integral is actually y equals minus 3 over 4 x squared plus 3 over 8x. And as we know that the general solution for this non-homogeneous ODE is the sum of the complementary function and the particular integral, we get that the general solution is y equals a times e to the power of x plus b times e to the power of 3x minus 3/4 times x squared plus 3/8 times x, where a and b are arbitrary constants. Again, this is a general solution. We could find a particular solution by subbing in initial values to get what a and b are. So I'll finish off with a couple of questions that I will not go through. Instead, this is your opportunity to have a go yourself. After I've written down each question, there will be a 5-second countdown before the answers are revealed. So question 1. We want to solve the second order linear ODE of d2y by dx squared plus 2 times dy by dx plus y equals sine x. Again, we want to solve for y. 5, 4, 3, 2, 1. Here the general solution was y equals a plus bx all times by e to the power of minus x minus 1/2 times cos x. This is because there was a repeated root and q of x was sine x, and therefore we tried a particular integral that was a combination of sines and coses. Question 2. We want to try and solve d2y by dx squared plus 9y equal to e to the power of 2x. 5, 4, 3, 2, 1. Here we get a general solution of y equals a times cos of 3x plus b times sine of 3x plus 1 over 13 times e to the power of 2x. This is because there was complex roots of the auxiliary equation, and our q of x was e to the power of 2x, so we tried an exponential particular integral. Thank you for watching my video.